Okay, thanks everyone for coming and thanks for the introduction. My name is Ranyiliu Chen, but just feel free to call me Chen. So I'm from University of Copenhagen, and yes, today I'm going to talk about this recent work with my PhD supervisor Laura Maciejska, and also a large group of people used around her or used to be around her. As the title suggests, this is not about building up new self-testing results, but rather to take a more careful examination of existing self-testing literatures and hopefully to lift common assumptions that have been made usually. Okay, so in this talk, I decided just actually this morning to put all the proof details and technicalities at the very end, just to make sure that I don't want to destroy your appetite for each. So anyway, so we're going to start with some background knowledge about games and self-testing in case you're not super familiar with it. And then we're going to go into our motivations, like why we want to be more careful about those about these assumptions, although it's usually made for whatever reasons. And why we think its definition is still kind of subtle, and what are the limitations of self-test? Okay, then I'll go to our main results, and also I'm going to mention about a very interesting example that we found in the quantum set of correlation, whose existence is not known before. Okay, so, and then finally, if we have time, we'll go to some proofs of the upper one. Okay. Yes, so in this very typical bipartite non-local game setting, or sometimes referred as fail scenarios, we have two players, Alice and Bob, who interact with the referee with classical inputs and classical outputs. Yes, so as a game, it consists of the two parts of the game rule, so which is the verification function is V, which determines whether the players win or lose the game. So they always cooperate. So it's not like a zero-sum game. So if they win, they both win. Yes, for example, in the CHSH game, this verification function gives value of 1 if the sum of their output is equals to the product of their input. Takes like 0. And still, we have this probability distribution that is referee or the verifier used to sample his question. In most of the cases, it doesn't matter, just the even distribution. Yes, and on the player side, since they are not allowed to communicate, their behavior is fully characterized by the states they share before the game and by the local measurements they perform on their individual part of the state. So we just put these three things together as a tuple and say, oh, this is the strategy that the players applied for this game. Okay. And with all this given, it is straightforward or trivial to compute or induce the game value from the strategy, also, of course, with the game rule. So we have this quite straightforward formula, but in the context of self-testing, we kind of want to do the opposite direction. We want to induce the underlying strategy employed by the player only from the game value that this referee can observe. Yes, so in this case, he can sort of classically verify the underlying quantum behavior of those players only from like classical communication. Yes, and here is self-testing. We only consider this optimal game value because just imagine if you have a game value which is not optimal, then you can always do like a combination of a better strategy and a worse strategy. So in this case, you can never induce what happens underlying. Okay. So and or in other words, we could say that this S is uniquely optimal for this game G. Okay. So this is just a definition of self-testing, and self-testing has actually found a wide range of applications in many areas. For example, in this device-independent cryptography, and also a bit surprising for me, it also is a very key ingredient in this breakthrough MF star called E, which shows its implication in complexity theory and operator algebra. Okay. Sometimes people even argue that its successful application has outpaced very careful examination of its mathematical.
Instead of applications in quantum computing or quantum algebra?
I mean, obviously, I mean, in many areas, like the process. But basically, crypto, but also some very surprising applications in operator algebra, for example. But still, many people believe that it is also a more careful, more examination of itself. For example, in the self-testing, we want to somehow show that some strategy is the unique optimal strategy for some game G. But what usually happens in the literature is that this uniqueness is only shown among certain strategies. For example, sometimes we assume that the employed strategy by the player, the strategy employed by the player, is a pure strategy, or the state is a pure state, because sometimes we can argue, oh, we can just purify the state, right? And sometimes people even assume that the state has full rank, which means the rank of the marginal state equals to the local dimension. In the pure state case, it just means that it has full Schmidt rank. Okay. So here is the very simple example. This maximum entangled state in C2 times C2 is, of course, full rank. But if we somehow embed the same vector into a bigger Hilbert space, for example, C2 times C3, then it's not full rank. Okay. Yes, and this is because we can't really see what happens outside the support of the state, right? Because if the state, for example, doesn't occupy the whole space of HB, then whatever you measure outside the support won't affect anything on the winning probability. And yes, also sometimes people assume that the measurements employed by as involved are projective measurements. This is because sometimes people argue that projective measurements or normal measurement is the only thing that our human beings can achieve at this moment at least. Or people can argue that we have this very powerful 9-mark dilation, which always gives you a projective implementation for any measurement. Right. Okay. So it seems that I made a lot of arguments that those are why we want to make those assumptions. But still, here I'm trying to convince you that it's better without. Okay. So the very first toy mode that I want to give you is this very simple example in entanglement. That is not self-test, but rather you can think of it as an easier task, right? Where you want to test some states are entangled or not. So imagine we have this perfectly correlated strategy, right? We have only one question for both players on which they have to answer always accordingly. So you can only answer with 0, 0 or 1, 1. Okay. So in this case, if we assume the purity of the state shared by S and Bob, then we come to a conclusion that this state must be entangled, because otherwise it's going to be a separable state. And if you perform local measurement on the separable state, you will never got any kind of correlation like this. Okay. So, but on the other hand, since this is only one question for each player, the correlation itself is a classical one, which means it can be implemented by, for example, shared randomness or separable mixed states like this. Right? So if we perform like computation measurement, basis measurement on this mixed state, we can still get a correlation. Well, of course, it's not entangled. Okay, so in this case, this purity assumptions really leads to a wrong conclusion of the existence of entanglement. Okay. And sure, to fight back the argument that I just mentioned like 5 minutes ago. For example, like we can always purify the state, or we can use dynamic dilation to the measurement. Yes, the point I want to make here is that sure, we can always do that, but for crypto purposes, especially for this device-independent crypto purposes, it might not be good. Because in that case, we can only say something about the purification of strategy or the dynamic strategy, but not the strategy itself. And still, I will be able to point to this perfect strategy and see what's going to be wrong in this crypto purpose. It's just to notice that it can be reduced by this GSS, right? Yeah, so if we look at the margin state on Alice and Bob is of course a maximum mixed state. But on the other hand, if it's a GSS state itself and the third qubit is held by like a third party Eve, then this Eve can eavesdrop the player's answers all the time, which means their output is not secure because it's predictable. Right? So this is not what we want in crypto, right? So yes, this is just another example where those yes.
Would you be able to say that in this case maybe your test is just insufficient? So I mean you can test if the state is entangled players by having them play CSSH.
Yes, you're right. It's just like a super naive example to give an idea why it could go wrong. I'm not saying that this is really a example where you cannot remove the assumption because, as you said before, the correlation itself is not the same. Right? So yes. What I'm trying to argue here is just to give you an idea of where it could go wrong. And actually, the good news is that we prove that in most cases it's okay to make those assumptions. But it's only because we prove that not it is true that it is true like a priori. Okay. Yes, the final argument that I want to make about those assumptions that it really goes against the philosophy of self-test. That's because in self-test we always say that it's the strongest form of verification because it makes minimal assumptions. But on the other hand, if you take like additional assumptions to like quantum theory and non-communication, then it's not the strongest. Right? And so in this sense, if we remove those common assumptions that's made in the literature, we can promote those results in its strongest form. Yeah. Okay, so that's the part about assumptions. Yes. Apart from that, we also find some subtleties in the definition of self-test. Yes. So yes, as I said before, in self-test we want somehow this optimal strategy is unique. But when we talk about uniqueness, there are always some kind of equivalence relation. We want that it is unique up to something. Right? For example, here there are several like trivial things that we can do to our strategy that doesn't affect its game value. For example, if we allow Alice and Bob to share more entanglement, but on which they never match, then it of course never gonna reflect to its winning probability. And also, if we allow Alice and Bob to like change their local basis or in physics language to change the frame of reference, of course it doesn't matter at all. And we can also allow SMBOB to embed their strategy into a bigger space, which of course will not affect its gameplay. Okay. So to try to cover all this sort of thing, people introduced different, I would say, or at least different looking definitions of self-test. Right. So here are the three things that usually being used in the literature. If you're not familiar with it, it doesn't matter what exactly does it look like. But the important thing is that different people do use different kind of definition of self-testing, and which is a bit annoying, right? Because it somehow reflects the fact that this definition is ad hoc. It's more like, oh, these are the three things that we can think of that is trivial. So let's put them all together to introduce this type of equivalence relation between strategies, and then we talk about uniqueness. Yes. So yes, and also we are not the first that is unhappy with that. There are already attempts trying to bring up better or operationally meaningful definitions for self-testing. But anyways, these three forms are the most commonly used definitions for self-testing in the literature. And so it brings up the very natural question. So are they really equivalent mathematically? Yes. Yes, so this is the issue of the definition of self-testing. And yes, for the limit of self-testing, we are really interested in what kind of strategy can be self-tested, right? And since the strategy always consists of states and measurements, this question can be broken down into two parts, like what state can be self-tested or what measurement can be self-tested. And the question for the state is, I would say, rather answered completely, because we, on the one hand, we already know that mixed state cannot be self-tested, and on the other hand, we know that all pure bipartite state can be self-tested. Yes. So the picture for states are rather complete, but for measurement, it's not quite so, because I think the most general result we know for measurements is we know that in this bipartite case, we know all real projective ones can be self-tested, and also there are some results in the multi-partite scenarios, which I'm not going to mention today. Yeah, but still we don't.
Is the proof constructive?
Yes.
So it's like you have a state and then you kind of build a non-local game.
Yeah, build a
and then
non-local
with
game.
that you find the optimal value and
And you build some measurements.
But you have to construct a non-local game.
Yes.
And same for the projective measurements.
Yes, and with projective. So given an arbitrary measurement, you construct other measurement and you construct the states, and you give a game such that it's a self-test. Yes.
Are they both together, like self-testing the states and the measurements, or can it be by separate?
Here we here the questions are considered separate. Yes, and I don't think we know how to.
I mean, my question is like self-testing. You kind of check like if the strategy that they are using is one, but like here you see that you separate states and measurements. Can you check by separate states? Are they using this state and measurements? Are they using these measurements, or do you have to check them both together, state and measurement?
In the definition of self-testing, we check both of them. Yes, but when considering what strategy can be
in that scenario that you have here, can you check them by separate?
Sorry, what do you mean by
just the state or just the measurements?
Here, I think it's both the state and the state. But the question is that in the self-tests of some, for example, on the left, when we were trying to come up with a strategy that self-tests a state, then you kind of construct some measurement.
Okay, thank you.
but then once you've done it, you self-test the whole strategy. That's all. Thanks. Yes. Yes. Just to come back to what I just said. Yes, the picture of self-testing measurements is not quite clear. For example, we don't know whether we can self-test or like genuine POVMs. Yes, so that's the limit of self-testing we care about. And yes, so this work we tried to come up with some answers to all the questions. Yes, so first of all, we show that existing self-testing definitions are equivalent in natural settings, which is simple and it's basically good news. So it means that when we talk about self-testing, we don't need to worry too much about it's definitely we just pick up whichever form we like. Okay? And another thing, which is actually the most non-trivial part of this work, I believe, is that we can leave those assumptions in most of the case of the literature, while we also identify the case where certain assumptions cannot be lifted. And for the limit of self-test, we show that which strategies cannot be self-tested. Yes, so basically we just show that non-projective measurement cannot be self-tested in some sense. Yes, I will go to the detail later. Yes, but the message is that we cannot really self-test POVMs. Yes, the last thing that I want to talk about today is that we find a very interesting correlation that has no full rank PVM realization. I think this is an this is an open problem for like 5 or 4 years as people raise that, and people sometimes even conjecture that it doesn't exist. So basically people guess that for any correlation we can always find a full rank PVM realization, but it's not true. Yes, so as we showed it.
Sorry, what is a full rank PVM realization? So full rank meaning what is it for a state with a full rank local interaction?
It means it is for the case in case of pure state. It means it's full full stream. Okay, so let's get to our main results. The first one is the simplest one. Just we show the equivalence between these 3 forms of definition of self-testing. We should show the equivalence of them. So yes, so basically we have this matrix form with which deal with this density operator and the measurement operator, and the product of them, which process in a matrix form. That's why we call it matrix form. And usually people work prefer to work with this purification form, where we only consider this purification of the state, so we can work with vector states rather than density operators. Also sometimes people work with this what we call the extraction form, because it explicitly says that this measurement operator is something rather than its action on the state is something. Yes, and it only makes sense when we assume full rankness, because if we don't, if we allow non-full rank state, then we cannot say anything about this measurement operator outside of the support. And we in this work we show that the matrix form and purification form are equivalent, and they are both equivalent to the extraction form in the full rank case. Okay, so yes, it's just a very simple message telling us that we don't need to worry too much about this definition. Okay, and yes, the most interesting part for the is for the lifting assumptions. Yes, so here to formalize our language, now I will take this T to be a subset of pure and full rank and PVM. So this is basically the assumptions we're going to make about the employed strategy. And we say a game is a T self-test if this strategy S is uniquely optimum among all T strategies instead of literally all strategies. Okay. So clearly with this kind of definition of self-testing with assumption, the inclusion of the subsets T gives us a hierarchy of the self-testing statement. Because, for example, if T is a subset of T prime, it means T makes less assumptions than T prime. Then, of course, T self-test would be stronger than T prime self-test. And in this sense, removing assumptions really means that we're promoting self-test into a stronger form. And it's just a matter of notation. If T equals a null set, which means we do not make any assumptions about self-testing, which is what we want, we will call it assumption-free self-test. So this is the strongest form of self-test in this language. And okay, then our result shows the following. Okay, so G be a normal game and S be a nice strategy for the game G. So here, nice means that strategy S is pure and full rank and PVM. So it has all the nice property that we want for a strategy. And we let it to be the canonical strategy of the game G, right? Okay. And now the A part of our theorem says, oh, if G is a pure PVM self-test for S, then it's automatically an assumption-free self-test for S. The implication from right to left is trivial. So it basically shows that pure PVM self-test equals to assumption-free self-test. So in this case, those assumptions could be removed without loss of generality. Okay. And then in this B part, we can show the similar thing. We show that if the G is a pure full rank self-test, then it's also a assumption-free self-test.
Sorry, the definition of pure PVM or pure full rank, because I have it like here for the strategies, but not for the game.
Yes, it's the assumption that we made for the strategy, and we say if we made those assumptions, then we say it's a.
No, but then you have it for the strategy. I mean for the game. So you have let S be that. Oh, that was sorry. Yeah.
Yes, that's the definition for T is self-test. Yes, so basically, if we made those assumptions, so basically, if we in our proof assume that the strategy employed by that symbol is pure, then we kind of show the uniqueness, and then we can only say that, oh, this is a pure self-test, but not like the assumption-free self-test. So that's the point. Yes, so this is basically our main results. This work, and I would like to comment here that this is actually corresponds to most of the case in the literature. Because in the literature, the canonical strategy is always nice. I would say it always has this very nice strategy, very nice property. Sorry. Yes. So basically, we kind of yes. So in this sense, we promote most of the existing self-test results into its strongest form. Yes, and then a few remarks I want to make here. The first one is the robustness is preserved. Yes, by preserved, we mean that if we start with a self-test with assumption, a robust self-test with assumption, then we end up with, again, a robust self-test without assumptions. Yes. So the property of robustness is preserved. But here I have to say that this epsilon delta relation dependence or its numerical robustness, it might blow up a little bit. I think it's in the worst case you need a square root. In some cases it is a constant multiple. So that's for the robustness, and also another thing I would like to remark is that this result also works for self-testing from Bell inequalities, which is also quite common in device crypto, I believe. Yes. So you can just think of self-testing from game as a special case of Bell inequalities, where the coefficients is front of measurement probability are just 0 and 1. Yes, and our result just applies to this more general case for self-testing from Bell inequality. Yes, and the main tool I want to briefly mention here is that the main tool that we use for this work is we look at the restriction and the Nyman dilation of strategies and yes, and improve some propositions about them. Yes, I will leave the details of the proof at the very end. It's just that yes, we believe that these technicalities might be of interest for people outside self-testing, because restriction and limitations are also commonly used, like in other areas, for example, in the study of quantum correlations. Yeah. Okay, then about this, we also leave an open question because here clearly these pure PVM and pure full rank assumptions are not the strongest assumption that we can make, or they are not the weakest self-tests. Right? In the most extreme case, where we put all of the assumptions to a self-test, can we kind of establish the similar things that we don't know? So the open question is that with a nice strategy as a canonical strategy, can a pure PVM full rank self-test imply an assumption-free self-test? That we okay, then let's go to our next result, which is about limit of self-test. As I said before, it basically tells you that we cannot self-test a non-projective measurement. But to be more precise, in this theorem, we show that if a game is an assumption-free self-test for some strategy S, then this S must be projective on its support. Or in other words, if this S is not nice or is a full rank but non-projective, then it cannot be self-tested in an assumption-free manner anyway. So this is the message, and it's because we also know notice that in this community, some people are also show some uniqueness about non-projective strategies, and yes, the point we want to make here is that here there must be some assumptions made. And finally, we will look at this very interesting example that we found in the quantum set of correlation. So here, yes, as I said before, there are canonical ways to give us like full rank strategy or PVM strategies, because we can always take the restriction of the strategy to its support, to the support of the state. Then we always get a full rank strategy, or we can always use Nyman dilation to the measurement to get a projective or POVM strategy. But somehow these two techniques somehow contradict each other, because when we take restriction, we end up with a smaller hyperspace, but when we use diamond dilation, we have a bigger hyperspace. Yes, and the question is, can we use both of them simultaneously to get a full rank and POVM strategy? And here we show the answers. So and the construction of the correlation is not complicated, I would say. So we will start with this canonical strategy of CHSHK, which consists of the EPR pair between Alice and Bob, and the poly measurement for Alice, and shifted poly measurement for which we call them H and G. Okay, and now let's consider another three.
Sorry, can you define G? Is it sigma x minus sigma z?
Yes, divided by square root. Yes, and now let's consider a third measurement operator, which is a three outcome but non-projective measurement, because Alice lives in the two-dimensional hyperspace, so it cannot be projective. But anyways, it consists of three POVMs, and 0, 2, and 2. And there are two equivalent characterization for those measurement operators. You can either think of them as a linear combination of Pauli's, or you can think of them as subnormalized Rancon projections. So from the left, we can show that they add up to identity. From the right, we can see that they are positive. So it gives us a valid POVM. Yes, but since yes, so now what we're gonna do is that we kind of plug this additional non-projective measurement to Bob's side, which means we ask Bob a third question, and on which he can answer three possible different. He can give three possible different answers. Yes, and then in this case, this P of S lives in the set of CQ232, which is the quantum set of correlation where we have two questions for Alice and three questions for Bob, and two answers for Alice and three answers for Bob. And note that this correlation cannot be assumption-free self-test by our theorem C. It's because we have shown that if this strategy is an assumption-free self-test, it has to be projective on its support, but since it has this non-projective M, then it cannot be assumption-free self-test. Okay, but the interesting thing is that it is self-test if we make proper assumptions. Yes. So in this theorem D, we show that this correlation has the following property. So first, it is extreme. It is extreme point in the quantum set. Okay, and then it is a pure full rank self-test for the strategy itself. And if we take non-modulation, then it's a pure POVM self-test. But as I said before, it's not a assumption-free self-test. And most importantly, this will imply that this P of X it has no full rank POVM realization. So it also, and then it also implies that in our main theorem, theorem B, just to remind you, in our theorem B, we show that if your canonical strategy is nice, then we can remove those assumptions. But here in our example or counter example, we kind of show that there is a case where S is not nice, then you cannot remove those assumptions. So the condition of S being nice is really critical in our main theorem. Yeah. Okay, so I think that's all I'm gonna say about our results today, just to quickly summarize everything. So our first theorem, in short, is that existing definitions of self-test are basically equivalent. And our next theorem states that if your canonical strategy is nice, which is also the case in the literature, then we can safely remove those many assumptions without loss of generality in self-test. And our theorem C says that if your canonical strategy is not nice, then we must be careful when we are talking about self-testing, because it's never going to be an assumption-free self-test. We have to make some proper assumptions for the failures. And finally, in our last theorem, we show that there is a correlation which cannot be produced by any nice strategy. Okay, so I think before I get to some technical detail of this work, this is a good time to ask questions. Yes.
Yeah, so I was a bit curious about, sorry, I misunderstood something about the definition of self-test, because in the start, self-tests were really something of a game, right? It's like you have just a value between 0, like 0.85, for example, and if you're close to that, you know something.
Yes.
But in your theorem B, you didn't talk about any tests as a game. You just talked about like the correlation, like a multi-dimensional object.
Yes, you're right. Yes, you're right. So basically, in B, there's nothing about games. It's just that we found the correlation that's not produced by any nice strategy. But we always try to kind of construct a game that self-tests these strategy with certain assumptions, but we don't know.
Okay, so if you would use the word self-test, can it also mean that you get the correlation and then want to find out the strategy, or is it always about the value of some game?
I think there's also some works like self-test from correlations.
So in your theorem C world, are you able to say anything about the relationship between the different non-projective or non-full rank strategies that achieve the maximum value? Is there some kind of symmetry between them?
Sorry, could you?
So your theorem C says that if I have a game whose maximum value is obtained by a non-full rank, non-projective strategy, then that can't be unique.
Unique in the sense we are in the definition we're talking about. Yes.
Yeah. So the question is, can you say it? Therefore, there must be several strategies that achieve that optimal value. So the question is, can you say anything about how they relate to each other?
I guess the point we want to make is that it could be unique if we make certain assumptions. It could be a self-test if we make assumptions, but it cannot be assumption-free self-test. It means that if we, for example, if we only consider, yes, so as we have some, for example, non-projective strategy, then it could be unique for all full rank strategy, but it is not full rank for any strategy. So it means that there are some different strategy, which is not full rank, and they achieve this same game value.
Exactly. So my question is, are you able to say anything about how that family of different strategies relate to each other? Is there some kind of symmetry between them?
We can. What we can say about it is that their restriction is the unique one, right? Because we can always take the restriction. Yes, but apart from that, we.
The self-testing results are often of the form something like if I have a protocol that gets me epsilon close to the optimal value, then the strategies involved in the protocol like epsilon close or 1 million epsilon close to.
Something like that. Yes.
Are you studying those kinds of robust self-tests, or are you studying perfect self-tests here?
We consider the robust case, yes, because we also established like the robustness of our theory.
Basically, my follow-up question is: if you start dropping assumptions, does the dependence on epsilon get worse?
Yes. The explicit dependence, epsilon delta dependence, it gets worse. But it's still. I think it's a square root.
It's a quarter for some of the assumptions actually. You need more conscious shorts essentially.
Square root for each assumption.
You mean in your the one with assumption?
I'm not sure. I need to check.
And in case of dropping the assumptions, is not for free then?
It is not for free. Yes. It blows up a little. Okay, if there's no further question, I guess I could go to some technicalities. I think I still have like 10 minutes before lunch. May I use?
Yeah, go for it.
Okay.
Good situational awareness.
Yes. So yes. Yes. What I want to say about the proof techniques is that in this our main theorem, theorem B, where we show that pure POVM self-test and pure full rank self-test, both of them imply full rank assumption-free self-test. We actually proved these three implications. So in the first implication, we leave this POVM assumption in this pure POVM self-test, and then we remove this pure self-test to get assumption-free one. And similarly, in the second part of our theorem, we first remove this full rank assumption, and we reuse the implication 3 that we established before to get assumption-free self-test. Yes, and here today I want to mainly focus on the implications number 1 and 2, because this is where we use heavily techniques that we develop about restriction and validation of strategies. Yes, just to give a quick definition. When we talk about restrictions, we can think of it as take the yes, because since we are here only working with pure state, we can assume that the state has a Schmidt decomposition, and in a restriction, we basically we just drop out this zero value Schmidt coefficient, right? Which gives us a isometry, maybe a co-isometry from your original paper space to a smaller one, and then we just sandwich it to all the measurement operators, and then it gives us a restriction of to the support of the states where the strategy will be full rank, right? And somehow in the naive we kind of do the opposite. We use a isometry from your original paper space to possibly a bigger one, and where all the measurement operators are projections. Okay, and first of all, we define some properties we believe that is crucial for strategies in this context. So first, we define the projectiveness of the strategy. It basically considers how projective your measurement is on the state. So here we use the state dependent inner product between identity minus between the identity minus A and A. And, yes, so this is how we define this projectiveness as just imagine if you have a perfectly projective measurement, then this gives a value 0. So it's basically characterize how projective your measurement is on your state. And
this is state dependent product.
Yes. So this the state.
How do you define this scalar product with that?
Yes. So it's the trace of X star Y. Or yes, and similarly, we want to define like the what something we call support preservedness, but it's really just a generalization of full rankness. So so imagine a case where your strategy is not full rank, but it's still but in this in the Schmidt basis, for example, this measurement operator has very nice structure. It has this block diagonal structure. Then in this case, this is also very simple because if we want to do the restriction, we just drop out this down right part, right? Yes. So in this case, it would mean that this projection onto the superlative state, which we denote by pi, is commute with your measurement operator. Sorry, yes, commute with your operator. Yes, and yes, so we just bound again this state dependent norm of this commutator to be epsilon, and we call the strategy epsilon support preserve. So this is basically a generalization of the full rank. Yes, and we will shortly see why we want this generalization. Okay, and the first thing we showed about these two properties of strategy is that both of them are invariant under local dilations, which is not surprising, right? Because in local dilation, we only allow like trivial things that we can do to our strategy. We only allow like change of local basis for attaching some state that we never measure, and of course those properties should be preserved under local dilations. So it means that if we have two strategies, one is a local dilation of another, and then if one of them is epsilon, for example, epsilon projective, then the other has to be also epsilon projective. And another thing that we show that if your strategy is already projective or support preserving, then its Lyman dilation or restriction is trivial. Right? Oh, okay. I just realized I forgot to define this notation beforehand. So this is basically this arrow, hook arrow notation, basically the equivalence that I mentioned before. So here the message is that yes, if you already have a for example, a projective strategy, then we still apply Lyman dilation to it. Then this dilation is basically trivial. You can think of it, you can understand it as a trivial thing, as a attaching trivial auxiliary and change of basis thing. Yes, and so this is it. And the last thing is that we kind of mix the ideas together, right? Because yes, okay, maybe I will say one more thing about the previous one. So here in this proposition or this property about those two things that we defined, we can already see why we want this generalization of full rank space, because we have a full rank state and we attach some non-full rank state to it, then it becomes non-full rank. So the full rankness is not preserved under these equivalence relations, but the support preservedness will. Yes, so this is why we want this generalization. Yes, and finally we show that yes, it is because yes, so this Lyman dilation is a canonical way to produce a full rank strategy, but it says nothing about its full rankness or support preservedness. Right? But here we should kind of show that if your Lyman strategy, your Lyman dilation is support preserving, then your original strategy has to be both support preserving and projective. And similarly, if the restriction of your original strategy is projective, then your original strategy has to be support preserving and projective. So I think this is the most important thing that we developed for restriction and Lyman dilation. And with all of them, we can establish our theorem quite clearly. For example, if we want to lift these PVM assumptions, we want to we basically want to show that PVM self-test will imply sampling-free self-test. What we're gonna do is that we start with any optimal pure strategy, and we take its NIMARK relation. Then, since it's a PVM self-testing, we have the equivalence relation between S NIMARK and canonical, the canonical strategy. That's two. Right. So this is from the PVM self-test. And the next thing we do is that we use our first proposition to show that this NIMARK relation is actually proposed. This is because we already, based on the fact that this S tilde is nice. Right? So this is why this but this is critical in our proof. S tilde is your canonical strategy being nice. So then in this case, your NIMARK relation has to be nice. And then with our last proposition, your general strategy has to be both projective and proposing. Yes, so that's pretty close. So finally, we just use our second proposition to show that the relationship between S and S NIMARK is really trivial. It's just they are just equivalent. So we kind of show that, and this equivalent relation is transitive. We kind of establish the equivalence between S and S tilde. So this is how we show that this, how we lift this PPM assumption. Okay, I think that's it. So thanks everyone for coming.